Section 2.4, Statements with multiple quantifiers. So our goal for this section is to go over statements that contain multiple quantifiers and discuss how to negate these statements. So in the previous section, we went over negations for statements that just had one quantifier, just the universal or just the existential. In this section, we're going to have a statement that's going to contain both the universal and the existential quantifiers. So in mathematics, formal logic, and computer science, it is essential that we all interpret statements in exactly the same way, since many important statements can contain both the universal and existential quantifiers. A convention has been developed for us to interpret them uniformly. When a statement contains more than one quantifier, we imagine the action suggested by the quantifiers as being performed in the order in which they occur. So let's consider a statement of this form here. For all x in set D, there exists y in set E such that x and y satisfy some property, p of x and y. To show that such a statement is true, you must be able to meet the following challenge. 1. Imagine that someone is allowed to choose any element x from the set D, and imagine that person gives you that element x. The challenge, number 2 here, the challenge for you is to find an element y in E so that the person's x and your y together satisfy the property p of x and y. So we have a predicate there with two variables. Since you do not have to specify the y until after the other person has specified the x, you are allowed to find a different value of y for each x you are given. All right, so to help us do this, I'm going to go over Tarski's world. So Tarski's world is a computer program that helps teach the principles of logic. Alfred Tarski, who's a Polish mathematician, he was the one that came up with this. But basically, in short, the program provides pictures of blocks and of various sizes, shapes, and colors, which are located on a grid, and then objects are given names such as A, B, C, and so on. So we don't have a computer program for it, so I'm just going to give you a static version of it, so just an image of a Tarski world, and we'll use that in our examples. Okay, so like for example 1 here, we have a Tarski world that's in that grid there. So we're going to consider the Tarski world that's shown. We want to show that the following universal existential statement is true. So it's a universal existential statement because that's the order in which the quantifiers appear. We have the for all here, the universal. So for all triangles x, there is a square. There exists a square y such that x and y have the same color. So you have your universal part there, you have your existential part here, and the property that has to be true is that they have the same color. So we want to show that this universal existential statement is true. So what I'm going to do is we're going to have given x. So that other person is someone else is picking out a value for x and giving it to you. And then you're going to choose, select a y value, but in a way so that the property is met. So in this first case, this first example, we're going to check that x and y have the same color. That's the property that has to be met. Okay, so for all triangles x. Okay, so how about our first triangle can be F. We have triangle F. We're going to list that here. So if someone gives you triangle F, can you pick what are we picking? A square. Can we pick a square y so that it has the same color as triangle F. And we can pick this square down here. We're going to pick square J. So if you're given triangle F, which is colored orange, you're going to pick square J, which also has the same color. So do they have the same color? Yes. And I'll just make a little note here. They're both orange. All right. Now let's say they pick a different triangle. They pick triangle G. Okay, so you're going to put G here in that column. Now, what are you going to choose so that your square has the same color as triangle G? So you just have to pick a green square. And there's actually two of them, so either of them would work. So we're going to put C or I. Check that they're the same color. Yes, both the triangle and the square are green. And is there any more triangles? Oh, we have K. We didn't check that one. So if someone gave you K, then we would pick J again because they would both be orange. So this universal, by building this table, we're showing that this universal existential statement is true. So for all of the triangles out there, you can come up with some square that's going to have the same color of it as it. All right, let's look at a statement of this form. So now you have the existential and the universal parts swapped. So now it says, there exists an X in D such that for all Y in E, X and Y satisfy some certain property. To show that a statement of this form is true, you must find one single element, which we're going to call X, in D with the following property. After you have found your X, someone else is allowed to choose any element Y from set E. That person challenges you by giving you that element. So it's your job to show that your X that you've already selected, together with whatever Y the other person chooses, satisfies the property P of X and Y. So your X has to work for any Y the person gives you. You are not allowed to change your X once you have specified it initially. So you can only select it once. So example 2, consider the Tarski world shown and show that the following existential universal statement is true. There exists a triangle X such that for all circles Y, X is to the right of Y. All right, so there is a triangle. That's your existential part. Triangle X such that for all, that's your universal part. So it goes in that order. There exists for all. And then the property is that X is to the right of Y. Okay, so we have to pick out one triangle X that's going to be to the right of all the circles Y. So let's see where we have a circle. Circle here, circle here, circle here. So this triangle not going to work because it's only to the right of circle B. It's not to the right of circle A or E. Can't use that one. This triangle, though, that will work because that's to the right of all the circles. And so will this one. That's also to the right of all the circles. So we're going to build our little chart again. Okay, so our table, we're going to have choose X. Given Y. And then we're going to check that that property holds. So we're going to check that X is to the right of Y. All right, so we are picking, and it looks like either F or K would work, right? So we're going to choose F or K. And then given A, circle A, that was this one up here, is your triangle to the right of it? Yes. What are the other circles? B? Is your triangle that you selected to the right of circle B? Yes. And then the last one was E, circle E. And is your triangle to the right of it. Yes. So you show that it works in all those cases. And that's it. So that's how you show that the existential universal statement is true. So interpreting statements with two different quantifiers. So kind of a summary here. If you want to establish the truth of a statement of this form for all x and d, there exists y and e such that p of x and y. Your challenge then is to allow someone to pick whatever x they want from set D, and then you have to come up with an element of value y in set E that works for that particular x. And in this case, what you pick is going to be based on the x value they pick first. And so your y value can change. But if we're doing the existential universal statement, so the quantifiers are in the other order. So if we want to establish the truth of a statement form, there exists x and d, such that for all y and e, p of x and y, then your job is to find one particular x in set D that will work no matter what y in E anyone might choose to challenge you with, and they're choosing that after you pick your x value. And maybe let's just go up to this one here. So for this x here, that's the set of triangles. X is in the set of triangles, and the y is in the set of circles, just to bring back that set concept. Example 3, interpreting multiple quantified statements. So Mikey, Joey, and Sam have the following closing options for the categories below. So for tops, they have long sleeved, short sleeved. For bottoms, they have shorts, pants, jeans. For shoes, Converse, jogging shoes, flip-flops, and for accessories, they have a hat and scarf. So that's what we're working with. So Mikey, Joey, and Sam make the following choices. Mikey here, he has short sleeve top, jeans, Converse, and a hat. Joey here, he has a long sleeve top, Converse. I forgot to put pants on him. And then Sam has shorts and flip-flops. Don't worry about Joey. So what we're going to do is we're going to rewrite each of these formal statements informally and then figure out the truth value. So we're going to write each of the following informally and find its truth value. So A here says, there exists a guy G such that for all items I, G chose I. So informally, this would be there is a guy, there exists a guy, there is a guy who chose every item, all items. I'll say all available items from that list, right? We had a list. And if you go back to the items, there is a couple options for tops, 3 options for bottoms, 3 options for shoes, and a couple options for accessories. And there's 10 items there altogether. And if we look at Mikey, Joey, Sam, no one's wearing all 10 items. Nobody chose all 10 items. So this is false. Now part B says, for all guys G, there exists a shoe such that G chose, or there exists a shoe S, I should say, such that G chose S. So if we look at all guys here, we're trying to figure out if all the guys chose some pair of shoes. So let's write this informally first. And this would be every guy chose some pair of shoes, at least one pair of shoes. And if we go to what they're wearing, Converse flip-flops, this would be true. So we're going to put true down. All guys chose a pair of shoes. That's why it's true. And then part C, there exists an item I such that all guys G chose item I. So this would be there is an item, or there is some item such that all guys chose it, or I'll put this even more like informally, there is an item that was chosen by all the guys, every guy. Do it like that. And then, is this true? So is there one particular item that each of these three guys selected? And it doesn't look like it. The closest we come to is probably the converse. Two of the three picked it. But this statement then is false. So you're going to write false, and then your explanation, no one particular item was chosen by every guy, by all the guys. And then we've got one more part D to do. So part D says, there exists a guy G such that for all category C, there exists an item I in C such that G chose I. So we're going to say there is a guy who chose at least one item from every category. That's what that's saying. There exists some guy such that for all the categories, there is an item in the category that the guy chose. And then, is that true? If we go back here, yeah, this is true because Mikey, for example, he chose a top, a pair of bottoms, shoes, and an accessory. So this is true. I'll just put Mikey chose an item from each category. So I have my explanation there. So many problems are stated in informal language, but solving them often requires translating them into more formal terms. So in the last example, we went from formal to informal. And now in this example, we're going to go from informal to formal. So we're going to rewrite the following statements formally using both quantifiers and variables. So for part A, everybody trusts somebody. Everybody, that's your universal part. So for all people X, somebody suggests like an existential. So there exists a person, somebody, there exists a person, Y, and then trust is like the property here, such that X trusts Y. So that's how you would write that more formally. And then part B, it says somebody trusts everybody. Now the somebody, that's the existential, the there exists. So we'll say there exists a person X such that, and then here's the everybody, so that's a universal, such that for all people Y, and then trust is your property, so X trusts Y. That's how you would put it into formal terms. Now we're going to look at negations of multiple quantified statements. So if we want to negate this universal existential statement, it's going to be equivalent to an existential universal statement, and we're negating that property, that P of X and Y, the predicate. So this part's getting negated, and you're swapping out your quantifiers. Same down here, if you're negating an existential universal statement, then the existential part becomes a universal part, the universal becomes an existential, and your P of X and Y just gets negated. So for example 5, we're going to write a formal and informal negation for each of the following statements. So for part A here, the formally, this is from the previous example, so formally this looked like for all people X, so the negation is going to be there exists a person X such that, and in the formal it said there exists a person Y such that X trusts Y, so that there exists part becomes the universal. So we'll say for all people Y, X, and then we're negating this, so does not trust Y. And then compare them, have these notes in front of you, look at the formal version of this. When you're writing the formal version of the negation, that will help. And then informally, what will this look like? This would look something like somebody trusts nobody. Right? The somebody, the there exists, the nobody, that's the for all, and it says does not trust. So we have nobody trusts nobody. And then part B, somebody trusts nobody. So when you're writing the formal negation to this, it helps to look at the formal version of this. So the formal version of this said, there exists a person X such that for all people Y, X trusts Y. So when we write out the formal negation, we're going to swap the quantifiers. So it's going to be for all people X, there exists a person Y such that, and then we're negating the property of trust, such that X does not trust Y. So that's the formal version. And then to write, and I should put formal here, and then to write this informally, this could look like nobody trusts everybody. You could also write it as everybody has someone whom they do not trust. That would be fine. And even for part A, if you go back to part A, the informal version could also, instead of saying somebody trusts nobody, you could also say there is somebody who does not trust anyone. That would also be okay to say. Okay, just a couple of comments. In a statement contain both the universal and existential quantifiers. Changing the order of the quantifier usually changes the meaning of the statement. And you can see that just by looking at the two statements from that last example we did. All right, we're done with this section. Make sure you do the homework, and I'll see you in the next one.